For those of you who don't know me, I'm Luc Moreau. I'm the head of the Department of Informatics, and it's my greatest pleasure to welcome Andrew Davison today. He's our speaker for this departmental seminar. He is professor of robot vision at Imperial College London, and he leads the Dyson Robotics Lab there. He was explaining me that this is not the same as the Dyson School of Design, which is an entirely different department. His lab is a lab in the computing department at Imperial. His research focus is on SLAM, Simultaneous Location and Mapping, and is really doing research towards spatial AI, the ability for systems to gain an understanding, a 3D understanding of their environment. And you can imagine how critical this is for robots. What is typical of Andrew's work is the practical dimension and the delivery of software and systems, and I'm sure he will present some of them today. He's been receiving awards from the major computer vision in the world, the European Conference on Computer Vision, CVPR, and also ICCV, so it's quite remarkable. He does translate his research into practical aspects. Apparently, if you've got one of those Dyson robots, the SLAM software to detect the environment is coming from his own lab, so that's quite impressive. He's also co-founder of a startup, SLAM Core, and you will not be surprised to hear that he's now a fellow of the Royal Academy of Engineering and a fellow of the Royal Society. So without further ado, I welcome Andrew.
Hi. So yeah, thank you very much for the kind introduction and for the invitation to speak here. So yeah, you'll notice the title I've got on my slides is slightly different from the one advertised. So I'd like to, I'll talk about spatial AI and SLAM in general, but also a bit of focus on something I'm very interested in at the moment and have been doing some work on that I think is exciting. So really just trying to think a bit of a vision towards a future of robotics. So let's imagine, 10, 20 years down the line, we might think that robots will become a major part of society, so possibly in many different areas, but let's imagine something like a smart farm of the future. Robotics may play a very important part in that. I think robotics is already coming into agriculture, but imagine, there might be, drones flying around kind of monitoring things. There might be wheeled robots going around planting and picking. There may be, definitely still humans involved with probably carrying some kind of smart devices, surveying and controlling what's going on. So I'm very interested in how a system like that will work. So especially if there are many different types of robots trying to really work together in an environment, how is that going to work? So one possible option, I think, is that all of those devices will be, talking to and controlled by some really centralized service. That might be, the future of a current maps type of system that we're aware of from the big tech companies. So clearly, if these devices, they need to know where they are, they need to plan action together. Does that all have to go through some central node, or is there a more sort of decentralized, distributed way of doing that, which might, have many advantages? It might enable a lot more innovation and different companies to be able to do their own thing. So I'm going to talk about that a little bit later on. But let's come back to the kind of core things that I've been interested in through my whole career, which is really this story of SLAM that Luc mentioned, simultaneous localization and mapping. How do robots know where they are in spaces and build representations or maps of those spaces? and taking that through to a bigger vision of something that we're now calling spatial AI. So I've been working on this research problem of SLAM, well, ever since my PhD, in fact, even kind of earlier than this date, back in the 90s when I was doing my PhD. But I was particularly focused on how can we do SLAM using the simplest possible sensor setup. And in my mind, that was always a single sensor if possible, so a camera. And can you do SLAM just with a single camera? And remember, this was at a time when SLAM was kind of a new thing, and lots of people were developing SLAM systems, but they generally involved complicated robots, quite unusual custom sensors, things like sonar, laser rangefinders. So trying to do it with a camera was quite new in those days. But of course, there was a lot of work in computer vision that we could build on. So in 2003, for the first time, I got this system working called MonoSLAM. Let me just show you an old video of this. So the goal of this system was real-time SLAM with a single camera. So SLAM means localization and mapping. So purely from the video captured from this camera as we're moving it around. So it's capturing video frames at 30 frames per second. We want to estimate the position of the camera continuously, but then we also want to build some kind of map or representation of the scene that it's in. And in fact, the fundamental character of SLAM is that if you're interested in either of those things, either localization or mapping, you have to solve both of them. So you need to build a map to help yourself localize, but you need to know where you are to help to continue build that map. So how does that work? So this is basically, as the camera is moving around, we detect and track within the scene things that we may think are going to make good, naturally occurring kind of landmarks in a scene. So what we didn't want to do was change the scene in any way. So clearly we could have gone around and stuck up kind of barcodes or something on the wall. We didn't want to do that, but it turns out that within most natural scenes, there are plenty of things which you can basically use as natural landmarks. So via some image processing, we can extract those things from the scene, and they tend to be, corner-like elements, so essentially high gradient image points in the scene. And as the camera moves, you can see that we can track those things. So now that means that for every new image that comes in, we've got a set of observations of which pixels in the image those natural landmarks occur at. And essentially that gives us a set of angular measurements which we can then feed into a probabilistic estimator. So here we're using a Kalman filter to then jointly estimate the motion of the camera and the 3D positions of those things. So that's what you can see visualized here. Here's the position of the camera, and you saw that was flying around. I've just paused it for a second. And here you can see the landmark position estimate. So each landmark, it has a little kind of texture patch, which is what kind of uniquely identifies it. But you can also see visualized here these ellipsoidal shapes, and this is representing the kind of output of the estimator. So this is the uncertainty in the position of that landmark. And you'll see that when we add new landmarks into a scene, they initially have high uncertainty, but as we make more and more measurements, that uncertainty reduces. So this was all running in real time, on a machine about 20 years ago now. And it turns out that this technology has been quite influential. I was certainly not the only person to have pioneered this kind of work, but essentially these kind of ideas have found their way into products that you can actually buy now. So my initial interest was always robotics. So even though, that demonstration I just showed you there didn't have any robot in it, it was just a human moving a camera around, but clearly the idea was if you can track the position of that camera and build a map, you can put that camera onto anything, so including a robot. So some of these products you can buy are certainly robots. So here's the one that was mentioned earlier. So there are now various robot vacuum cleaners you can buy that actually use SLAM. So this is the one that I was personally involved in working on. It's from Dyson. It was in fact their first ever robot product that was released on the market. There's now a series of these from Dyson. So this it has obviously Dyson's high power cleaning system, but what they didn't want to do was early robot vacuum cleaners were essentially very simple, and they would basically almost randomly move around your room and over a long period of time hope to find their way into all the different corners and clean them. Dyson didn't want to do that. They wanted a robot that was much kind of smarter. So ideally, a robot that would be very systematic and clean every part of a room exactly and then know when it had finished. So in order to do that, the robot needed to know where it was. So that's where SLAM comes in. So using this camera, as the robot's driving around, it captures images like this. And this is actually an unusual, it's a camera that captures a 360 field of view. So that's actually really good for SLAM. But what we use those images for is exactly the same thing as we did in MonoSLAM. We detect natural landmarks, like things like the corners of pictures and furniture that happen to occur in any normal room. We make a 3D map of where those are, and then we also simultaneously estimate the motion of the robot. So in this application, the position of the landmarks is not really very important. We don't really care what they are or where they are. We only care that they are stable points in a room that enable localization. So the important thing is where is the robot, because if you know where the robot is, you can then remember everywhere you've been, you can clean in this systematic pattern, you can know when you've finished. But they're very much the same technology as that is used in various other types of products. Some of these you might not think of as robots. So one kind of major area, for instance, is in the tracking for augmented reality and virtual reality headsets. So this is a video from Oculus. So she's wearing a VR headset, is immersed in some kind of virtual world, playing a game. For that game to be compelling, whenever she moves her head, the virtual world has to move in the correct way. So in order to enable that, we need accurate head tracking. And the early versions of these headsets, when they came out, you would have to put some kind of special apparatus in the room that would track the headsets. The latest ones work using basically visual SLAM. So this headset has cameras inside it, and it builds exactly the same sort of map of natural landmarks in the scene, which are the things that enable the tracking of the device. There's also fusion of other sensors, so that inertial sensors are also an important part of the tracking here, but they combine with the vision system within this full SLAM estimator. Very similar technology. It also runs in smartphones. You can get apps that, where you can scan a room, for instance, and also in things like in drones from companies like DJI or Skydio using visual SLAM, so you can do things like, very accurately move them around, tell them to come back to where they started and things like that. So these are products that you can buy, but I would argue that they're still kind of quite early products. They're still fairly niche devices at the moment. But I think that this technology is growing into something bigger. So this term, spatial AI, kind of represents a vision of where this technology is heading towards, not just positioning technology. It's heading towards a computer vision type of artificial technology that will enable any device to be aware of the space around it. And as that becomes more and more capable, we should be able to enable more and more powerful products and applications. So one way of thinking about that is thinking of layers of capability. So level 1 capability in SLAM might just be where am I localization. Level 2 might be much more kind of detailed mapping of the scene around me. So not just this sparse set of landmarks, but actually capturing detailed geometry of the whole room or space around me. The level above that might be semantic understanding. So this means not just geometry, but actually building maps that have meaning and are aware of objects and so on. So if you can really go through all of that, I think we might get to some really powerful products. So for instance, the kind of things that I'm interested in working on with Dyson at the moment, would be, very general home robotics. So a robot vacuum cleaner is really the only home robot you can buy at the moment that's actually useful. But imagine a robot you could buy that would actually tidy up your kitchen or your dinner table or something like that. That's a dream product. I think lots of people might be interested in that if it existed. It doesn't exist. No one knows how to make it yet. And I argue that it's because this technology isn't advanced enough yet. So let me just talk to you a little bit about some of the progress through those layers of capability that we and others have been working on. So this, for instance, is a demonstration of a dense SLAM capability. So this was this is a system called Elastic Fusion that we published. This was like 7 or 8 years ago now. So it's a similar kind of setup to the first video you saw, in that we've basically got a handheld camera device being moved around in a room, and without any other information, we're trying to jointly estimate the motion of that camera and then build a map of what it's seeing. But you'll see that the map now is not just a sparse set of points in the scene, it's this really detailed geometric map. So one thing to note is that this is a camera that captures both color images and depth images, so it is a Kinect style camera, although we can now do quite similar things to this without needing the depth channel, in fact. I'll show you some more about that later. But it is a SLAM system in that this kind of shape you can see flying around here, this purple shape, is the estimated position of the camera. So we're simultaneously estimating that motion and then fusing all of the kind of information we gather into this 3D dense scene model. So when we're trying to reconstruct dense geometry like this, there's actually many different ways of going about it. So how do you actually represent dense scene geometry? In this system, we use something called a circle representation. So essentially, elements of the map are little disks. So each disk has a 3D position, an orientation, and a color. And if you kind of splat enough of those close together, they join up into a continuous surface. There are plenty of other different ways of representing 3D geometry, like meshes or like implicit functions on grids and things like that, or occupancy grids. And we've tried different, probably all of them, and there's lots of interesting pros and cons there. So that's a detailed, dense map, but it's still just geometry. There's no kind of sense of meaning there. So you can see the sort of shapes of objects emerging, but the system doesn't really know that this is a chair or this is a table. So that's one of the kind of other things we've worked on a lot recently, and is very much, I would say, a current area of research in this area in computer vision. So how can we build semantic representations of scenes that have both geometry and meaning? So this is clearly an area where advances in machine learning and deep learning are coming into SLAM and being really useful. Although I think it's very important to note that this area of kind of 3D vision, SLAM, has not been entirely taken over by deep learning, like some areas of computer vision. There's still plenty of old-fashioned and probabilistic geometry and estimation going on. But I think we've been able to build some really interesting systems by putting elements of deep learning into this kind of more geometric estimation framework. So semantic fusion was one of the first things we did in that direction, and actually it's quite a simple system. So it's the dense SLAM system you saw in the previous video, building a detailed representation of the world out of circles, and then we're also sending the images that we capture into a deep neural network, which has been previously trained to do semantic segmentation. So you can train a neural network to report for every pixel of an image what it thinks the object class present is there. So is this pixel part of a chair, part of a table, part of a wall? And then essentially we take a set of those frames that we're using to build the map, we feed them also into the neural network, and then we take the reported labels from the neural network and we fuse them back into our 3D map. So each circle in the map might be observed by multiple images. It might be labeled various times, and then we kind of probabilistically fuse those labels such that each circle now has an estimated class. And that works kind of somewhat reasonably well, I would say. So in many ways, it comes down to how good is your single view neural network, but you can do a bit better than that because you get multiple views of each part of the scene, and you can fuse somewhat inaccurate estimates to get something better. But still, we tend to get a somewhat kind of messy result. I should say this one on the left is a ground truth view, which has been hand-labeled, which we're then comparing against. So yeah, we certainly still get some errors. It's kind of a bit noisy. And also, it's important to note there's no sort of sense of separate objects in this system. So it's really like we've taken our 3D map and we've kind of painted it with, a semantic texture and say, well, this area is chair and this area is floor, but there's no concept of kind of separate chairs in this system. So that kind of area is another one that we've worked on. So I think trying to move towards that kind of object level representation of a scene. So this is one example piece of work we did called Node Slam. Let me just go back here. So the idea of this system is that we want to directly build a map of this scene at the level of objects. So specifically in this demo, we're considering 4 different types of objects that we're interested in. So we've got cans, bottles, mugs, and bowls. So each one of those types of objects, we have some prior information about it. So we've got actually a data set of CAD models of mugs. So for instance, we've got 500 CAD models of mugs, and they're all sort of slightly different shape. But from that data set, we have learned basically the average shape of a mug and the main modes of variation of the shape of a mug. And that's all represented in actually a 3D variational autoencoder. So that means that every time, so as we move our camera around and we detect mugs in the scene, so we might, we're using a kind of off-the-shelf object detector to say, well, it looks like there's a mug present in this part of the image. Then we bring in our kind of mug shape model, and then we optimize the parameters of this autoencoder in order to make our 3D mug model fit the information that we're observing. So here's a kind of longer image sequence here. So we're moving the camera around, and you'll see we detect new objects. They kind of pop into the scene here, and then you'll see their parameters get optimized so that the shapes and positions of these objects will adjust a little bit until they match as well as possible the different observations that we're getting. So, simultaneously, we're estimating the motion of the camera within this system. So it's a kind of a SLAM system now where instead of the kind of elements of the map being these arbitrary points, the elements of the map are now actually these objects, which have, they have known identity, they have, shape and position. And this is actually now a really sort of, both efficient and useful representation of this scene. So clearly it's not capturing everything, it's only making a map of the objects that we've kind of pre-programmed it to be interested in, and obviously extending that to all objects in general is a really hard challenge that I think is a current research issue. So let me just show you another quick part of this video where we show what that might be useful for. So this is, again, the sort of things we're very interested in my lab at the moment. So moving towards more general robotics for the home. If you want to go beyond cleaning the floor, you're going to have to deal with objects, and you're going to actually have to pick them up and do things with them. So here we have a demonstration where there's a camera, mounted on the wrist of this robot. It makes some observations of the scene. It detects and fits models of these objects, and then it can actually use that knowledge to then plan some action. So here we're actually now going to tidy up this scene. We're going to place all of the bowls into a nice, neat stack here, and then we're going to pick up the mugs and place them into nice, neat positions within the box. So I would argue that this quite kind of explicit 3D representation of objects and shape is really, strongly enabling for this type of manipulation. So you might see a lot of robot manipulation demos that go as far as picking up some objects and maybe just dropping them in a bin or something. But if you actually want to precisely place an object or, use it for something, maybe use it as a tool to manipulate something else, I would argue, it's really powerful to have detailed 3D understanding of its shape. And then you can do this really kind of precise stuff, like putting objects away in your cupboard at home. Anyway, still plenty of work needed to make manipulation really work, but it's a really interesting challenge. So I'm just show you a couple more things really on this side of thinking about the representation of 3D scenes, also thinking about how concepts from machine learning are coming in to help us in how we design SLAM and spatial AI systems. So there's a couple of papers we've worked on recently that I think are very compelling in this area. So especially, this is quite an unusual idea when I first heard about it, but has become quite widespread. You might have heard of papers called NERF, which is a really well-known thing in computer vision. So that stands for neural radiance fields. So it's the key kind of idea there is to represent 3D information in a scene explicitly using a neural network. So we've made a kind of a version of NERF, which is smaller, faster, and actually works in real time. So this is a system called IMAP. So in IMAP, same goal as ever, same goal as Elastic Fusion. We've got a handheld camera moving around in a scene. This is actually also a depth camera that captures color and depth. And our goal is to track the position of the camera in 3D and to build a map of the scene. But the way we represent the 3D map here is really very different. So the map is explicitly represented by a neural network. So it's a quite simple MLP, multi-layer perceptron network. And it's a network that has an input, which is kind of a 3D coordinate, and an output, which is representing the color and the density of that point in the scene. So i.e. by density, we mean if it's empty space, it should be a 0. If it's part of an object, it should be 1. So if you've just randomly initialized some neural network and feed in a coordinate x, y, z, you'll get some kind of garbage output because all the weights are all over the place. But if you gradually train that network based on observations, you can gradually make it better and better represent a scene. So when we've got a camera in the scene, and at some point in the scene, we capture a color image, we capture a depth image, and then we render from our neural network. We say, well, based on our neural network representation of the scene, what color and density do I expect? What color and depth do I expect from this camera viewpoint? And you do that by basically shooting rays into the neural network, querying it many times and saying, if I look at the density and find out if I integrate the density and find when it gets to 1 and then read off the color, that's the color that I should be observing here. So now clearly with our randomly initialized network, we won't get that, but then we send a training signal back that says change the weights of the network somewhat such that we are rendering close to what we get. So this is our current observation, this is our current rendering, and we're training the neural network to make these more similar to this. So we keep doing that as we keep moving the camera around. This is a more sort of global 3D view of the neural network representation of the scene. It starts off looking very messy. There's all these funny kind of clouds hanging in the sky. Everything looks a bit kind of loose. But quite quickly, and what's really interesting in this system, this happens in real time, over a period of minutes. So, this video is a little bit sped up, but not that sped up. This does actually converge, on a desktop GPU within 2 or 3 minutes to quite a useful representation of this scene. Let's just skip forward a little bit. So here you can see now the camera has observed, most parts of the scene, and we're getting this quite sort of realistic looking representation. So compared to NERF, which is this, algorithm for doing this offline, you can get these, super precise looking representations of scenes. This is working in real time. It's quite a small neural network. And we also do some sampling to make it all run fast. That means we're not getting quite the same precision. But I would argue that this is possibly, still a quite interesting representation of 3D scenes. So it doesn't necessarily have the accuracy of something like Elastic Fusion, but what it does have is a nice property of being quite kind of complete. So, any kind of holes in the data just tend to be quite nicely filled in. So just the fact that this is generated from a neural network gives it this sort of smooth, coherent property. So it's a good argument. If you want a robot to do something in a scene, what property of the representation do you need? I think most people would agree you don't need a millimeter precise model of a room in order to start tidying up. You probably need to know roughly what's there, where most of the objects are, and then maybe when you go to actually pick something up, you'll locally get that real detail information. Anyway, so very, very interesting ongoing work there. I'll just quickly show you a couple of other videos. They're not actually incorporated into my presentation because these are a bit like, I mean, they're actually under submission to CVPR right now, so this is sort of hot off the press stuff. But the papers are on archive. But just a little bit more in this area of machine learning meets SLAM. If you're kind of into what's going on in computer vision, you may have also heard of Gaussian splatting. This is a sort of very current idea in 3D representation that's also being used a lot in 3D vision and graphics. So here the idea is that you can represent a scene with many, many Gaussian blobs, basically. And people are showing this has some nice, it's much, much faster than NeRF, for instance, but can also get really detailed representations. So we've built one of the first SLAM systems that uses this 3D Gaussian splatting representation. And we're able to show, so this is actually using a monocular camera, so there's no depth measurement here, but just from a single camera flying around in a scene, we can actually reconstruct now this almost photorealistic representation of a scene. And I'll just show you one more video of, this is again very, very current work. So here again, we're using a neural network which looks at images and decomposes them into quite useful sections. So some things that are working quite well now in deep learning-based computer vision. One is segmentation. So this idea that you've got an image and you feed it in and it will segment it into chunks that represent objects. There's this thing called the segment anything model, which is a really, really powerful image segmentation tool. There's another neural network we're using which can look at an image and estimate the normals at every pixel. So that means the kind of vector direction of the orientation of the surface at every pixel. So if we can segment a scene into some regions, and then we can also estimate the normals, that's what's being visualized here, we can kind of turn that region into a little, quite accurate 3D chunk. So now, just doing that for a single image doesn't immediately tell us the 3D shape, because when we just see a 3D chunk in the scene, we don't know the depth. So we don't know whether this thing here is something that's small and close or big and far away. We have this uncertainty. But if we've got another image of the scene, we can test all of those different hypotheses of how far away this chunk is and see which of those is photoconsistent with other views. So anyway, again, as we always do, we've kind of turned that into a kind of SLAM system. So here, for instance, is just an example where we've got 3 images of this scene. The middle one we've segmented and turned it into these chunks. And then by optimizing the kind of depths of those chunks to make them photo-consistent with some other views, also estimating the positions of the cameras, we're able to build this quite compelling 3D representation. Okay, so I wanted to just show you those. So very much kind of hot off the press work in 3D SLAM and representation. Okay, so getting back a bit to the original discussion here. So spatial AI, I think it's coming. It's going to be more and more important and generally useful. I've written a couple of quite kind of high-level discussion papers called Future Mapping 1 and 2 about my kind of thoughts in this this direction, which I recommend if you're interested in this. I still think there's a lot of work we need to do to get to the sort of full spatial AI that might really enable these very ambitious products. And I think especially, some of the limitations there, they're not just that the algorithms don't do everything that we want them to yet. They're also that the algorithms are very kind of heavyweight and expensive at the moment. So if we really want to enable, mobile robot products, for instance, or, wearable devices, we can't have all the computation done on massive GPU clusters in the cloud. So I'm really, really focused on the kind of efficiency of these systems. So this is just a kind of rough diagram of the sort of system complexity. So don't worry about any of the details, but the blocks of computation and the massive amounts of data that need to flow around a system like semantic fusion, it's quite complicated. So we've definitely seen this thing happening over time of a system that ran in real time on a big desktop machine, some period of years later will be running on your phone. So something like MonoSlam, when I first published that, it was running on the biggest PC I could buy in 2003. And 10 years later, clearly that can run on a phone. 20 years later, it's probably running on a tiny embedded chip somewhere. But even so yeah, to make these things more efficient in general, and we've got orders of magnitude of improvement. So for instance, to make something like smart spectacles that could actually have a full AR capability, we're probably 3 or 4 orders of magnitude away in terms of the power requirements. So actually the way that the algorithms we use for this kind of stuff evolve together with the hardware, so specifically I mean the processing hardware that they run on, has become very interesting to me. So we had a project in that direction which ran over a few years jointly with the universities of Manchester and Edinburgh. So really thinking about SLAM, the algorithmic components, and then how those run on different sorts of processors, right from at the high-end kind of big desktop system with big GPU down to a local tiny embedded board that runs on really low power. So which parts of our algorithms work well? And so some of the things that I really learned from that project are, if you want to really make algorithms that run at really low power, one of the most important things is to try and avoid moving data around too much. And I think that really implies moving away from the standard sort of von Neumann model of how a computer works, where you've got a processor here and memory here, and you're kind of shunting everything backwards and forwards all the time. What we need to move towards, we definitely need to embrace parallelism, because we're going to need to do more and more computation. We can't just run processors faster and faster anymore. We hit this kind of a heat wall. So we're going to have to embrace parallelism, but a more general sort of parallelism than we currently have on GPUs, I think. So more and more towards sorts of processors that co-locate processing and data, and as far as possible kind of store things and operate on them locally and have a minimum amount of sort of communication between them to keep everything synchronized. So this slide is actually from a company called GraphCore, which is this UK computing processor startup based in Bristol. They have a product called the IPU, Intelligence Processing Unit. You might also call it a graph processor. So it's a massively parallel chip. It has thousands of processing cores on the chip, but each one of those cores has its own kind of quite significant amount of local memory and can run incredibly fast by doing operations on that local memory. And the memory is actually on chip, which is different even from a GPU. But also then it has a quite impressive kind of interconnect structure on chip. So what's also quite efficient to do is to pass messages around between those different cores. So they can all be running quite different programs. So unlike a GPU where every kind of thread is doing the same thing, they're all doing quite different things, operating on local memory and then sending messages to kind of synchronize. So I think that kind of pattern is a very powerful one for the future, and maybe how computing will go in a more general way. These are some of the visualizations from GraphCore of how they're currently mainly selling their chips as deep learning kind of accelerators. You can take all the operations that happen in training or doing inference on a neural network and compile down and find the graph-like structure. That's what this is visualizing in these cooler pictures. So kind of inspired by that, I've been thinking about SLAM and spatial AI and thinking where are the graphs in SLAM, both in terms of representation and computation. And you can clearly find some really easily. And in fact, graph-like structures evolve very naturally in SLAM. So, for instance, there are representation of a 3D world. There's a natural sort of locality that nearby things kind of connect to each other and connect relatively, things that are far apart connect more weakly. So in order to take advantage of that, a computation that might have that kind of non-local distributed pattern, we need to have algorithms that match up to that. So this is where I've got very interested in algorithms that can really operate in a non-local way. So that thinking, which we've already done some work on, actually involving processors and actually running some efficient SLAM processing on an IPU, But that thinking is what really got me into this. So looping right back round, once we're thinking about distributed processing and algorithms that can really have many sort of separate processing elements that then talk to each other and everything gets consistent, I started thinking, well, okay, that could be many kind of threads within a single processor, or it could be many devices that are all kind of talking to each other via some kind of mesh-like networking. So imagine that each of these devices has its own local processor, its own kind of local idea of what's going on, but then it's able to communicate with some of the other devices that are nearby without ever needing a kind of global server. So that's really what we've been focused on in this kind of work. So we've got a paper called Robot Web, which is thinking about this problem, but specifically thinking about the localization problem. So, localization, where am I, in the end is probably the, I'm not going to say it's the most important thing, but it's really important in anything you do in robotics. And, that SLAM, 20 years of SLAM work has proven that to me. If you can reliably solve that where am I question, it's useful for so many things. So how might that work in this system? Okay, so knowing where you are in a space based on measurements that you make from your sensors is fundamentally a probabilistic estimation problem, because all of the information you get from your sensors is going to have uncertainty and errors. So we're going to solve it using probabilistic graphical models, and in particular this formulation called factor graphs. So this is from a paper, an excellent review paper by Frank Delert. So there's this general formulation of things I want to estimate and things that I can observe can be represented as a factor graph. So here, for instance, is a factor graph for SLAM. In SLAM, if I've got a single device moving through the world, observing some landmarks, the things I want to know are the positions of the device as it moves. So these T1, T2, T3 are kind of historic positions of the device as it moves. And then L1, L2 are the positions of the landmarks in the scene. So those are the kind of unknown things I want to estimate. These would be the variables in my factor graph. But then the information we do know is represented by these black nodes here, the factors, and these are basically the observations. So for instance, this might be a visual observation. So I observed the image coordinate of landmark 1 from camera position T1. And then I also observed the position of the same landmark from position T2. So that's an observation. These are some numbers basically that we know from our sensors. We might also have direct observations of the motion. This might be from an inertial sensor. It might be from wheel odometry or something like that. So factor graph inference is the problem of going from knowing the black ones and not knowing the white ones to the other way around, so wanting to know what the white ones are. And there's basically many algorithms for doing inference on factor graphs. And classic ones, you can think of a Kalman filter as one sort of algorithm for doing this, or bundle adjustment, nonlinear optimization is a sort of full batch solution to the whole thing. But it turns out that there are distributed ways of doing this. So let's think about what the factor graph is for multi-robot localization. So the assumption is that we've got several robots moving through a scene, and they observe each other sometimes. So the green robot is moving around. These green circles here are representing position estimates of the robot at different times. What are the observations it makes? First of all, these black factors are local motion observations that would, again, come from wheel odometry or something like that. So even without looking at the other robots, it's got some knowledge of its motion. But then there are also these factors that connect one robot to another. So for instance, at this time here, this robot made an observation of robot 2. So maybe it's got a camera or some other sensor, and it says, oh, look, I can see robot 1 over there. And robot 1 has some special thing about its appearance that means it can identify it. And it measures the distance and the angle to robot 1. So that's what's represented by this measurement. So that's the factor graph for multi-robot. If we can take that factor graph and kind of upload it all to a cloud somewhere, we can run any sort of solver, and we can get the solutions for where are all the robots. But we're interested in doing this in a distributed way without needing a centralized server. So the algorithm that's really come to be useful to us is a set of algorithms, especially that are well-known classical algorithms called belief propagation. So these are algorithms that go back to the 80s and stuff, but have actually, I would say, been very much out of fashion recently. And especially, they're not necessarily very good algorithms for running on a CPU. There are better ways of solving these problems if you've got all of that information on the CPU. But the great advantage of belief propagation is it can solve these problems in a distributed manner. So especially, we've got interested in Gaussian belief propagation, which is the special case where all of these variables have Gaussian distributions, and we can also model the factors as Gaussians. So that turns out to be a really good general assumption. It's more or less the same assumption we always make in SLAM, and has turned out to be very useful. So we've written an online article, which I'm just going to briefly show you. So if you go to gaussianbp.github.io, this is it's an interactive article. So rather than just writing, a kind of PDF paper about this to introduce it generally, this is in the style of this. There's an online machine learning journal called Distill, which was around for a couple of years. We got really unlucky because we submitted this paper just the week they announced they were going to close it down. So it never made it into Distill, but I think it's of that quality. But just to show you one of the things that's built into this, so it's a visualization of something like a robot web type of problem. So imagine 9 robots here that are observing each other in this pattern according to how they're connected by these lines here. So that defines a factor graph. We can solve this factor graph with Gaussian belief propagation by passing messages. So the kind of way this works is each one of these nodes only needs to store a local part of the factor graph, and then there are rules for how you pass messages. So one way of passing messages is like this. So if I press synchronous iteration, at every step, it's like every robot simultaneously sends out some messages to its neighbors and then receives some messages from its neighbors. You'll see that we don't have to iterate that too many times to get to the correct solution. And this kind of comparison between this and this shows that we get exactly the same solution that we would using a kind of joint batch solver on a single CPU. We can get exactly the same solution with this distributed solver. But even more interesting than that is if I hit this random message button. So rather than sending synchronous messages, we can just pass random messages. So this means every time I press this button, we randomly choose a robot and we randomly choose a direction to pass a message in. And in fact, we can, if we do this enough times, and clearly this is not as efficient as the synchronous iteration, but we will still converge to exactly the same solution. So that's an amazing property of Gaussian belief propagation, distributed asynchronous convergence. And that is very much the property that I would argue we need for this kind of robot web application. So just going back to this picture here, how do we implement Gaussian belief propagation, therefore? It's quite simple. We have think of taking the whole factor graph and then drawing a dotted line around each part of it. And so basically the part inside the green dotted line is owned by robot 1. The part inside the red dotted line is owned by robot 2. So each robot owns some fragments of the whole factor graph, and then it carries on message passing within its own fragment, so that's no problem because this is all within robot 1's memory. But then when it needs to pass messages across these dotted boundaries, that's where we're going to need communication. But here we have the great advantage that the communication can be asynchronous. So all that robot 1 needs to do is kind of publish all of the latest outgoing messages that cross its dotted line on something like a web page. So imagine that each robot has a web server. They communicate with each other over Wi-Fi, so whenever one robot gets close to another one, it will read its latest web server, copy all its latest outgoing messages that cross this dotted line, see which of these messages are for me. So clearly if the red robot reads robot's 1 web page, it's going to take this message, and this message. It's going to then incorporate those into its own message, internal message passing, and then publish its updated outgoing web page. And what the web pages look at are they're quite small tables of numbers, basically, because they only concern small parts of the factor graph. So you put that all together, and that gives you this robot web system. So in fact, this has just recently been, although we did this work a couple of years ago, it's finally been officially published in IEEE transactions on robotics just in the last month or two. But here we've got a simulation demo of this running. So of course, this is not a true distributed implementation because this is running on my laptop, but it's a simulation of a distributed system. But it runs really fast, even on my laptop. So here's just a first example where we've got a set of robots here, and we want them to all drive in circular trajectories around this arena. So maybe I'll just start running that. Let me just turn a couple of things off to make it clearer. So we've got all these robots, and they're following circular trajectories. Now, each robot, it has some internal kind of odometry sensing, so it can estimate its motion, but in a way that's not completely accurate. So if you only were doing that, these robots would drift. But also, it has the ability to observe other robots that are nearby. So if I turn this on, this pattern of lines is the observation pattern. So actually, there are some fixed landmarks in the corner here. So these beacons are some fixed information about the scene that all the robots know about, and those serve to kind of anchor the coordinate frame. But you'll see that only the robots with the largest radii ever get close enough to these landmarks to actually directly make observations of them. The ones that are more, closer to the inside, they never see the landmarks, but they do see each other. So there are lots of measurements here of robots measuring each other. So the other thing to show is this is basically the communication pattern. So robots obviously need to communicate with each other, but they don't need to communicate anything like all-to-all. So in fact, on each step, each robot randomly communicates with one other, and it will tend to communicate more likely with robots that are closer to it. So this is a bit simulating what a kind of ad hoc, Wi-Fi mesh type network might look like. So at the moment it's hard to see, what the localization is actually doing. But if I temporarily turn off the sensors, so here I'm going to set the sensor range to 0, and you'll see that the robots stop making measurements of each other, and you'll see that what was actually going on here is that each robot, we're drawing two things. There's an estimated position, and then there's a ground truth position in the simulator. So when they're not measuring each other, those things quickly diverge. If I just turn the sensor back on, you'll see then the measurements kick in, and the robots will snap back into these accurate positions. So yeah, it's fully distributed, very, very dynamic, and very, possibly widely useful, I think. So quite excited about this work. So that's Robot Web for localization, but the last thing I want to show you, and this was a bit of a surprise to us, is that you can actually use a very, very similar method for planning. So planning in robotics means deciding where you're going to go next. So a simple planning problem for a single robot might be, I've got some current known position here, and I want to get to some position over there. Now, the way that I'll do that so this is a kind of local planner. I will plan a sort of sequence of steps that I think will take me towards that goal. Now, you have to be aware of some constraints there. So the first type of constraint is normally to do with the way that your robot can move. So robots can't just sort of jump around randomly. They normally have some dynamics constraints. So therefore, consecutive positions in my plan should be related by the dynamics constraints. So the robot overall will have to move in a kind of smooth way. So if I only had a goal and some dynamics constraints, probably I'll plan a straight line motion to the goal. But if I'm also aware of some obstacles and things I need to avoid, so for instance, I want to get to that position there, but I'm aware of that chair, I will also connect my intermediate kind of states to that obstacle with a constraint that says, I don't want to get too close to that obstacle. So you can think of it a bit like a spring kind of extending around over there, but being pushed away from this obstacle. And if you then optimize that, you find the path that most satisfies all those constraints, you'll get this smooth path that goes around there. So that's single robot planning. What about multi-robot planning? Well, it turns out that the kind of the graphical representation of a multi-robot planning problem looks very much like this. So each robot plans a path into the future where these black kind of nodes would now sort of take the role of, planning, dynamics constraints. But then we have inter-robot factors that say, I shouldn't crash into another robot. So we, essentially, we can solve these. So as long as we have all of these constraints as kind of square-type quadratic constraints, it turns out that the solution to this is mathematically identical to Gaussian belief propagation. So let me first show you a little video of this. So here we've got an example where we've got some robots trying to cross a junction. So here you'll see two robots, and then these kind of smaller green dots are their plan for the future. So the robots have the global goal of just moving forward, and as long as nothing gets in the way, that's fine. But when the robots start to get close to each other, we create factors between kind of future steps of the robot at equivalent times that basically say, these two should not be too close together, and these two should not be too close together. So because these robots were due to crash, some of these constraints won't be happy, and they'll push those future states a little bit further apart in the solution, and then you'll see that everything else will just get adjusted. So this all happens quite smoothly. So what essentially happened there was the two robots, sped up or slowed down a little bit such that they would avoid each other. So here's what happens with 4 robots, no problem. And here's what happens with loads of robots. So yeah, is this the future of traffic management? Would you ever get into a car that was doing something like that? But yeah, clearly this is the possible, exciting future of things like autonomous vehicles that are actually communicating with each other and jointly planning. So here with this, nice advantage that we don't necessarily need a central server, although, what's the kind of reality of this? What are you really going to trust what everyone says and so on? So, so anyway, that was almost something which we did just for fun. It seemed quite easy after the robot web thing. And in fact, we've got open source code that implements this if anyone's interested in playing with it. Okay, I think I'd better finish there. So I've talked about a lot of things. I think, especially related to the robot web work and this distributed things, I think these web-like interfaces that enable possibly this kind of collaboration between multiple devices without needing to know too much about each other. So we called this robot web, very much inspired by the World Wide Web. So this, Tim Berners-Lee said, if you can have, you define HTML, HTTP, and all the computers in the world can talk to each other, that's turned out to be an incredibly powerful idea. Is there going to be an equivalent for robotics? So meanwhile, definitely going to continue working on this whole big spatial AI mission, and I think we're going to be doing that for quite a few years yet. So both at the Dyson Robotics Lab, which is my academic lab at Imperial, and then, I'm also involved with SlamCore, which is a London-based startup that has applied solutions in this area. Okay, let me finish there. Thanks very much. Yeah, do we have some questions?
Okay, thank you very much for the insightful talk. I will open the floor for questions. Are there any questions? Yeah.
Hello, that's a great, very interesting presentation. So I was just wondering, I think one of my friends was, working on a localization problem. And I guess it's in a warehouse context where a lot of the stuff was looking exactly the same. And he was sort of struggling to sort of tell let's say localize is sometimes he saw this robot thinking was in the first floor, and then sometimes it was on the third floor because the doors looked exactly the same. So in this sort of multimodal sort of problem, do you sort of believe that your sort of robot sort of network graph sort of communicating solution can sort of solve this problem, or do you think that there's a problem with his algorithm, or is it that it's a technology issue, basically?
I mean, it's a very well-known problem, of course, in localization. if two places look identical in the end and you've got no other information to disambiguate, yeah, there's fundamentally no solution to that. Now, of course, either your sensing gets better and there's something about those scenes which makes them different and you can eventually differentiate them, or you've got some other prior information that will help. So to be honest, getting confused between which floor you're in, assuming you know where you started and you know when you've gone up and down in the lift, that should be enough to resolve that problem. Or maybe you've got some other sensor, maybe you've got a pressure sensor that gives you enough information, roughly am I 2 or 4 meters up, that might be enough. So I think, in most practical settings, some sort of sensor improvement or sensor fusion can be enough to resolve that. But yeah, fundamentally, if two places look identical and you get lost and you just see what's around you, you don't know. And you're going to have to temporarily say, well, 50-50, I might be here or I might be here. But then maybe I'll go out the door, make some turns, see what I see, and something will come up that will resolve that ambiguity.
So yeah, that makes sense, thanks. Yeah, I think he was trying to experiment with like multimodal Gaussians at some point, but I think
exactly,
yeah,
so temporarily hold multiple hypotheses and try and resolve it later, yeah.
Cool.
Thank you. Okay, Yalian, thank you.
Thank you. Thank you for the very wonderful the talk. So, and also some very interesting demos. So I'm very interested in the last junction demo that you just showed. So you mentioned that these vehicles could collaboratively negotiate to avoid collisions. I just want to understand a bit more about how the negotiation works. What kind of languages does these vehicles use?
I mean, it's Gaussian belief propagation. So literally, it's a direct implementation of that. So I guess, yeah, the way you can think about it is each robot has its current future plan with this set of poses that it thinks it's going to end up. And those are the things that send messages across to the other robot will have its future plan. And yeah, those will be linked by factors. So messages will be passed across those factors. So definitely, as that iterates and converges, you can think of it as negotiation. But yeah, there's negotiation happens implicitly, across the whole network of robots that are talking to each other. And so, it's a complicated thing, right? Because if I see I'm going to collide with that robot and I slow down a little bit, but then that might then put me into a colliding path with this robot over here. So ultimately, to solve it, you've got to solve a joint optimization problem, and it would be very hard to kind of just hand code an algorithm to do that. But it turns out that Gaussian belief propagation is a distributed way of solving that kind of full joint optimization problem. And so it's very powerful.
Yeah. It's great. Thank you.
Yeah.
Hi, thank you so much. I had some questions about kind of how you found sensors lately. So full disclosure, I'm a bit out of date. The last time I looked at this was 2019, so obviously there's been a lot of changes. Mm-hmm. I did see in one of the demonstrations you had a clear pint glass. So I was wondering how you found sensing and then processing clear objects and surfaces. So something like a pint glass and then also a puddle of water. Mm-hmm.
Yeah, I mean, those remain very difficult challenges. So, depth cameras will not necessarily work very well on those type of objects. I think, an area where progress has been made recently, so, I showed you one video where we were reconstructing some glasses and stuff. So the Gaussian splatting method. So, these methods that are now actually reasoning about light fields. So, the thing about a glass that makes it difficult to deal with in computer vision is that its appearance, very much depends on the direction that you look at it from and the lighting in the scene. So these methods are actually reasoning about that. So they're actually really trying to reconstruct the light field, and they're aware of the fact that different surfaces will have different appearance from different directions. So, Yeah, but I would say still far from being solved, and just pure sensing is not necessarily going to solve it. So, you come back and think, how does a human reason about, a glass or a shiny object? Yeah, not sure. There's those kind of little hints, the kind of glints that you get from reflections, the way that as you move, you see it, maybe slightly, you see the colors you can see through the glass gradually change. They give you these kind of cues about its shape. But yeah, hard ongoing problems in computer vision, I would say. Probably more likely to be solved algorithmically than by completely new sensors.
Thank you so much.
Mm-hmm.
Hello, yeah, thank you for the talk. Now, in the last problem where you were talking about multi-agent planning, I would assume in safety critical applications where you have multiple agents in very near locality, you would have to presumably perform synchronous propagation between the agents. Now, I would assume that even in the case of maybe even 10 agents or something, it probably becomes intractable really fast. The propagation of information. So how would we deal with that?
Yeah, good question. So you would argue that to be safety critical, you probably do need all of the agents talking to all of the other agents all of the time. Maybe. I guess what we've found is that the algorithms will still converge quite well, with a much less communication than that. But I think you're right to ask the question if you really wanted to put some sort of, safety critical stamp of a guarantee onto an algorithm like that. I don't know, to be honest. It may still be that you need some sort of trusted arbiter that's really aware of everything. It may be that you need to install at each junction, some safe thing that doesn't let a vehicle in unless it knows somehow that it can be trusted, because all you need is one vehicle that's, run by a terrorist or something, and is lying about its location. Are you ever going to drive at 70 miles an hour into a junction unless you can fully trust somehow what's going on? No, I mean, good questions, and our work on this is at the kind of fun demo stage rather than anywhere close to an implementable solution.
Thank you so much for your presentation. So in your presentation, you mentioned that through an ordinary camera, you can measure where the objects are and then kind of provide 3D mapping of those objects. So I'm particularly interested in 3D mapping of buildings. So especially projection mappings for purposes. So I was wondering if there are open tools or platforms to which you can upload videos or videos taken by drones, for example, where you can come up with the 3D mapping versions of those buildings.
Yeah, I don't immediately know off the top of my head whether there's anything openly available that does that really well. I mean, clearly that sort of technology exists. How do they build Google Maps or whatever, that has now really detailed 3D models of lots of buildings. I think it's a combination of, software that combines, I think they probably use aerial images together with the ground-based kind of street view images, a certain amount of fully automatic 3D reconstruction, probably still with some kind of manual tweaking, I expect at the moment, to get it looking really good. I don't know, to be honest, what the sort of best thing you could just download and do that kind of thing is at the moment. I'm not sure.
Thank you.
We have time for one last question, and then we'll discuss what happened with the social.
Thank you. I just wanted to maybe follow up on the comment about is it maybe safety critical for all the agents to talk to each other? that would be presumably provably like NP hard, right? So I would argue that it's maybe a defense of this approach is to say what's safety critical and something we can actually do in practice is going to have to be achievable, right? It's going to have to be a tractable solution.
Yeah.
And if this is the best tractable solution, then who cares that we could do better by solving an NP hard problem? That's not really relevant.
Interesting, yeah.
Which brings me maybe to the question I actually wanted to ask, which is I was surprised a little bit to see belief propagation like playing such a central role, given that it's this very kind of classical approach from quite a while ago. I was wondering if your group had looked at any probabilistic circuit solutions to this, because that's kind of where a lot of the tractable probabilistic modeling is now. It's very much built on belief propagation, sort of all these factor graphical results from like the 90s, but it's implemented it with a slightly different, trying to balance sort of tractability and expressivity a bit more generally.
Probabilistic circuits, yeah, it's not a term I'm very familiar with, to be honest. I'd be interested to hear more about that, but is that, so it's like message passing, but around more?
It's a general class of like graphical solutions that was built on these sort of 90s results from,
maybe you can send me a link or something. Sure. It may be something that I know of by a different name I guess, previous work in SLAM has definitely, based on passing messages around graphs and things like, for instance, trying to find the closest tree to a general graph and then doing things like that. I guess this sort of belief propagation is at the far end of not wanting to, pure sort of distributed. Each node doesn't really need to know anything about the whole structure of the whole graph, and then probably belief propagation type things are the best you can do, possibly. But I guess as you allow more global knowledge to be shared, then you can clearly do more efficient things. But yeah, I'd be really interested to hear more about that.
Thank you.
Okay, thank you. This concludes the Q&A session. I know there are many more questions from the audience. So I would like to thank the speaker once again. Thank you very much, Andrew.